Hi everyone, we'll start with electric field lines. Electric field is a vector and there is certain way to represent this electric field on paper. The figure which you're seeing is an example of field lines given out by positive charge. Well, there are arrows. Here you can see arrows, right? You observe that the length of the arrow gets decreased as you move far from the charge. Well, this means that the electric field is getting reduced as you move away from the charge. And the direction of these arrows gives the direction of the electric field as well. Now you may get a question, how many number of lines should I draw? That really doesn't matter. Actually, you can draw any number of lines, and please note that there are no lines actually. This is just a method of representation. So it really doesn't matter how many ever lines you draw. Well, take an example. Maybe this is the figure you draw, and this may be the figure your friend draws, which is correct. Both of them are correct, but it's not the number of lines that is important. It is the relative density, or you can say the closeness of the lines that is important. See, take a small area here and take the same area here. You'll see that the number of lines passing here is more than number of lines passing here. Well, even in your friend's diagram, you'll observe that the number of lines passing here is less than the number of lines passing here. That is what is important, not the number of lines. Actually, you are living in a 3D world, right? So, the charges emit these field lines in all the directions. So, what you're seeing on the screen right now, uh, you get the same picture or same image through any plane which is passing through an isolated charge. Actually, this concept of field lines was given by a scientist named Faraday for visualizing electric fields. Now, these field lines have some definite properties. Let me discuss them. Well, take a positive charge, and the field lines always go out of a positive charge. And if it is the case with negative charge, field lines go inside the negative charge, the direction. This property is about direction. You might be wondering about the heading. This is a shortcut I created because in my childhood I had this problem. I had a confusion between these two. This shows that out of positive and into the negative. So field lines go out of the positive charge and go into the negative charge. Hope this is helpful. And let's go to the next property. Field lines never cross each other. See, uh, let me tell you something. The direction of the electric field is given by the tangent at any point on the electric field line. So, if this happens, I mean, if really two electric field lines cross each other, say, now, how do you get the direction of electric field at this point? Is it this way, which is the tangent to this curve, or is it this way, which is the tangent to this curve? Sorry, my diagram is not so clear. If two electric field lines cross each other, then you will have two options for getting an electric field, for getting the direction of electric field, which is rubbish actually, because at any point electric field is unique. So this should never happen, right? So that means that field lines never cross each other. Let's go to our next property. Field lines are continuous without any breaks, unless and until they are interrupted by some charge. See, if this is your charge, you get some field lines. They are continuous. They may be curves, but they are smooth curves. If they are interrupted, it means that there is a charge here. Yes, this is possible. But unless and until interrupted by a charge, they are continuous. Let's move on to our next property. Actually, not property. Uh, Basing on these properties, you'll observe that, see this example. When two positive charges are placed near each other, you'll see something similar to this. These are the field lines. And see, observe this positive charge. Both are positive charges, right? So electric fields are going out of them, and no field line is intersecting any other thing, and all the curves are continuous. And see this example. When a negative charge is placed near a positive charge, you'll see that field lines go out of a positive charge and go into the negative charge. No field line is intersecting any other thing, and they are continuous as well. Next topic is electric flux. How to start it? Okay, see this. Say you have you have some water flowing through the tap, and if you place a ring here, you can calculate the amount of water flowing through this ring per second, right? And if you place the same ring in this manner, you'll observe that the amount of water flowing through it per second is reduced. What we're going to deal is something similar to this. Well, how to explain flux? Normally people say that flux is the number of field lines passing through a surface. Well, it is right, but it is wrong. Let me tell you. If it is the number of field lines passing through it, uh, anyway you'll get to know how to find the flux by the end of this video. And by chance, say you got an answer of flux as 17.2, say. Well, if it is number of field lines passing through a surface, then you have 17 lines, you have 18 lines, but what is this 17.2? It is meaningless, right? So that's what I'm going to say. It's not, flux is not the number of field lines, but those people who explain it as number of field lines, they explain it because it gives a good intuition for us. Actually, even I'm going to explain using the same method, same regular method. But just note that it's not number of field lines. It's just a way to explain. It's just a way to get some intuition for what's actually going to happen there. For few minutes, you assume that the flux is nothing but the number of lines passing through a certain area. Well, take this example. If you have some E in this direction, and you have a surface here. Well, if I increase the surface, more number of lines pass through this surface, right? So you can say flux is something similar to this. So you can say electric flux is proportional to the area. Let me call it delta S. And if the field itself is stronger, you can say more number of lines pass through this surface. So it's also proportional to E as well. Now, if I place the same surface in this manner, something like this, number of field lines get reduced, right? By what amount? Take a perpendicular here. Say I tilted it by an angle theta. Well, area is a vector, you know that, and the direction of this area is given by the normal vector, which is perpendicular to the surface. Say it is n. If this is theta, then this is going to be theta. So it gets reduced. I mean, it gets multiplied by this cos theta, which is less than 1. So it gets reduced. So you can say this is the flux. So if theta is something like 90 degrees, it means that if this is your electric field, your surface is something like this. So no electric field line passes through the surface. So flux is 0. And you know this is you know how to calculate this flux for a surface, right? A normal surface. But what if you have a surface like this, some curved surface? Then what to do? Divide the surface into smaller and smaller and smaller parts, infinitesimally smaller parts, and if they are so small, they can be approximated as normal surfaces, normal planar surfaces, and calculate the flux and add them up. You'll end up with the answer. Just now I said area is a vector and its direction is given by the normal vector perpendicular to it. But a surface has two normals. Say if your screen is your surface, then your normal vector may be going into the screen or coming out of the screen. Then what to do? Which one to choose? If you are getting that question, then it's better you follow a convention. The normal convention says that if you are dealing with a closed surface, then the normal vector which is pointing outwards, it is taken to be the direction of this area element. So now you know that flux is E delta S cos theta, which is nothing but the dot product of electric field and this area vector. And I can write it as E delta S cos theta. Actually, there are two ways to read it. You can write it as E times delta S cos theta or E cos theta times delta S. Both of them are correct, but this means that the number of field lines passing through the projection of area element onto the surface which is perpendicular to the electric field lines, and this means that the number of field lines or the component of electric field passing through the area perpendicularly, or the component of electric field which is normally falling on the surface. If you understand both of them, I'm really very happy. It doesn't matter even if you don't, because anyone gives the same answer. There are just two ways of understanding it. Let me move forward. We'll solve a small problem. And the problem is we have a coordinate system x, y, z. Let me name it x. This is z, and this is y. We have an electric field in this positive x direction. It's given by alpha x power 1 by 2. Alpha is some constant. It is given as 800 Newton per coulomb per meter per 1 by 2 something. And the side of the cube is a, and it's given as 0.1 meter, and it is placed at a distance a from this origin. So now we have to calculate the flux through the cube. Well, flux through the cube, to calculate the flux through the cube, we have to add the flux on all the surfaces. But luckily, what happens here, since the flux is pointing or flux is directed towards this positive x direction, the flux on the top, bottom and front and back surfaces is 0, because their normal vectors or area vectors are making 90 degrees with this direction of electric field. So we don't have to worry about this. We'll just concentrate on left and right surfaces. Let me share them. Now, first let us calculate the electric flux through the left surface. Let me call it phi L. This is given by electric field at left surface and its dot product with area element, that is the area of the left surface. Note here, the direction of this area of left surface is towards the negative x-axis. This is it. And electric field is this. Why is this to the left side? Because I just said by convention, in a closed surface, the area points outwards. So the theta here is 180. So, and EL is alpha, and put x is equal to a here. We get alpha e power 1 by 2. Since cos 180 is minus 1, put minus here, and a square is the area. Similarly, for the right surface, you get it something like this. Alpha 2a, here it is 2a, right? And the area is same again. Now, add these both things. Say to calculate the flux of the cube, let me name it phi c, which is nothing but phi L plus phi R. If I add these both things, I'll get alpha into a power pi by 2 and root 2 minus 1. Put values of a as 0.1 and alpha as 800. We'll end up with 1.05 Newton meter square per coulomb. This is the unit of flux, and that's it for today. Bye.